to gravity. Thank you. This is the governing equations. First equation represents the continuity equation, mass conservation. The second equation is the momentum equation. The left side is represent the inertia force. The first term on the right hand side represent the viscous force, and second is the buoyancy force. And third equation represent the energy equation. The first term on the left hand side represent the net energy due to mass transfer, and second term on the right hand side represent the conductive heat transfer, and second is the viscous distribution parameter. We consider the temperature dependent thermal conductivity which is proposed by Charadu is kappa equal to kappa infinity 1 plus delta T F minus T infinity. This equation 6, this is the dimensionless, we use the dimensionless variable this. With the dimensionless, when using the dimensionless variable, then we get the coordinate equation, momentum equation, and energy equation, and we get the three parameters. Number one, the thermal conductivity variation parameter, the control number, and viscous distribution parameter. And this is the boundary condition for using the variable, and here this is the another parameter T. T is the conjugate parameter, and the present in distribution we consider T equal to 1. Here we use the side system function, equate the similarity variable, and H theta is the surface temperature, and H is the dimensionless temperature. Then we use this, we get the two equations. The first equation, the equation 12, is represent the momentum equation, and second is energy equation. Our present result compared with the Koji and Lupo and Martin and Cobb, we observed that this table, our present more closer to the Martin and Cobb. Results and discussion. This figure is thermal conductivity variation, velocity of thermal conductivity variation, and temperature of the thermal conductivity variation. Here, gamma equal to del Tb minus T infinity. Gamma depends temperature difference between temperature outside of the surface and temperature of the outside of the fluid. Gamma depends on this temperature difference. When temperature difference increases, then gamma is also increases. That means the heat moves from plate to the boundary layer. Then it increases the temperature increases within the boundary layer, and rapid mass transfer. That means the velocity increases. We also seen that the velocity increases for the increasing thermal conductivity variation parameter, and temperature increases for the increasing thermal conductivity variation parameter. As a result, we observe when the velocity increases of thermal conductivity variation parameter increases, then the skin friction increases for the increasing value of thermal conductivity variation parameter. And when as a result, surface temperature increases for the increasing values of thermal conductivity variation parameter. This is the velocity profiles against N for the viscous distribution parameter. Here we observe the velocity increases for the increasing values of viscous distribution parameter, and as a result, when the increasing velocity increases for the increasing values of thermal conductivity viscous distribution parameter, as a result, we observe the skin friction increases for the increasing viscous distribution parameter, and surface temperature increases and increasing values of viscous distribution parameter. Yeah, this is the velocity against theta of Prandtl number. Here Prandtl number is represented the kinematic viscosity ratio of the kinematic viscosity and thermal diffusivity. Prandtl number is a proportional to the viscosity. That means when the Prandtl number increases, then viscosity increases. So viscosity when the viscosity increases, then the velocity decreases. That means when the Prandtl number increases, then the velocity decreases. We observe the figure that decreases velocity for increasing values of Prandtl number. When the velocity decreases, then we observe that the skin friction decreases, and also surface temperature decreases. Conclusion: the velocity and temperature within the boundary layer increases for the increasing value of thermal conductivity variation parameter and viscous distribution parameter, and decreasing values of Prandtl number, and skin friction of increases of the increasing values of thermal conductivity variation parameter and viscous distribution parameter, and decreasing values of the Prandtl number. The surface temperature increases for the increasing values of thermal conductivity variation parameter, viscous distribution parameter, and decreasing values of Prandtl number.
Thanks for presenting, and I would like to also